So, in the last module, we had in sufficient detail seen the similarity solution, and we had brought the expression for the similarity equation. That is, we had said that for flow over a flat plate, the governing equations become this way. This is a third order ordinary differential equation in eta with the boundary conditions as follows: y equal to eta corresponds to eta equal to y equal to 0 corresponds to eta equal to 0, where u is equal to 0 or f prime of 0 equal to 0. Then we said as y tends to infinity, that is eta tends to infinity, u is equal to u infinity or f prime of infinity is 1. And the third boundary condition was at y equal to 0, eta equal to 0, v becomes equal to 0 because of no slip, and from the expression of v, from the expression for v, which was obtained as v is equal to half u infinity mu by x eta f prime minus f. So, no slip condition demands v equal to 0, f prime of 0 equal to 0 or eta equal to 0, whatever. So, at eta equal to 0, this term is 0 and this term is 0 necessarily. Therefore, this has to be equal to 0, and that is your boundary condition, f of 0 equal to 0. So, these three boundary conditions for this ordinary differential equation is what you see for flow over a flat plate. This is flow over a flat plate with a free stream velocity u infinity, which is equal to constant. U infinity equal to constant means dP by dx is equal to 0. The pressure gradient parameter m is equal to 0. U infinity, recall, is Cx to the power m. When m equal to 0, you get flow over a flat plate. This whole set of equations, remember, we had a differential equation, we had a set of differential equations which looked like this. You had a set of differential equation which looked like this with m plus 1, so on and so forth. So, f double prime times m plus 1 plus m plus 1 by 2 f double prime plus m times 1 minus f prime squared equal to 0. This was my ODE. When m equal to 0 you got this equation. So, this values of m being 0, m is equal to 1, m is negative, m greater than 1, all these things represent, these represent flow situations where this is called as a problem of wedge flow with the central angle pi beta. This is a wedge flow problem. Faulkner-Scan solution is something that you would have seen. This is flow around a wedge, correct? When pi beta with central angle pi beta, when beta is equal to 0, that is dP by dx equal to 0, we get flat plate. What was my beta? Remember, recall this definition, m we got as beta over 2 minus beta, or beta is equal to 2m by m plus 1, or beta is equal to, you got an expression for beta also in terms of the m, got an expression for beta in terms of m. So, whatever way you use, you can write an expression for beta or m. When m equal to 0 or beta equal to 0, it represents flow over a flat plate. When beta equal to 1 or the wedge angle is pi. It represents the case of flow hitting a vertical plate, and this is called as a stagnation flow problem. Stagnation flow problem, u infinity is Cx to the power 1, which is Cx. So, stagnation flow is another class of problems where you have flow hitting here, reaching stagnation point, and then u is equal to C times x. So, along the direction as the jet spreads out, u infinity is going to be equal to C subscript f. This is another class of problems. A third class is or you can also say when dP by dx is negative, which is called as favorable pressure gradient. What is favorable about it? As flow happens, or for flow to happen, that means if any real flow has to take place, flow happens from high pressure to low pressure. Heat transfer happens from high temperature to low temperature. So, dP by dx necessarily has to be negative, hence it is called as favorable pressure gradient. This is, if this is there, then flow is going to happen. So, this corresponds to beta greater than 0. So, when I write, remember, dP by dx is equal to minus rho u infinity du infinity by dx. This being negative, du by dx is positive. dP by dx is positive. This is called as adverse pressure gradient. This is not good for the flow. Beta is negative, and therefore, beta is negative, your case where beta is less than minus 0.2, this one. This would lead to flow separation. Beta less than minus 0.2, flow separation would occur. That means, why I am telling you all this, though we had a general differential equation. So, we got an equation ODE was z triple prime plus zz double prime plus beta into 1 minus z prime squared equal to 0. The f equation was transformed to the z equation, okay, and vice versa. If you look at it both ways, this, when you go back to this expression, look at this one, okay, m was directly related to your beta, okay. So, ideally speaking, on paper, this equation for different values of eta of beta or m should have meaningful solutions. What we are trying to say now is, similarity method, the way it works is that not all, remember the conditions, when I use a similarity variable, after using the similarity variable, the governing equations and boundary conditions should transform in such a way that there is no dependency on the old independent variable x and y. So, all the coefficients that are there after you derive the ODE, all the coefficients or number or terms which are there in the boundary conditions should be constants or only function of the new dependent variable eta. That was a big restrictions. Having worked through the restriction, we come to an ordinary differential equation which looks like this, that is f triple prime plus whatever, and subjected to several boundary conditions. This m is called as the pressure gradient parameter, and what we are saying is, this gives us a family of solutions for m being greater than 0 to m being less than 0. m is equal to 0 is one special case which happens to be the Blasius profile. M negative and M positive, which corresponds to favorable or adverse pressure gradient, is also going to be talked about. dP by dx is equal to positive is adverse pressure gradient that leads to a flow separation. So, I keep on making beta minus 0.05, 0.01, 0.1 minus 0.15, all this go on making it negative. When beta is equal to minus 0.2, you get flow separation. That means you get, what is flow separation? The velocity profile would become such that du by dx would be equal to 0. So, du by dy equal to 0. The velocity profile would be such that the shear stress would, you would have the flow then taking an opposite direction, because the momentum of the flow, it is as if you are trying to climb a hill, and if you do not accelerate, your vehicle is eventually going to stop and it would even be pushed backward. If you do not accelerate, if you are going at 40 km per hour and trying to climb a hill, your speed is going to go on reducing because of the gradient. That is this dP by dx. The gradient is positive, which is not helping you move. So, the fluid is also subjected to a reverse kind of action, and the momentum, the velocity of the flow is directly indicator of the momentum. So, if you look at the left hand and the right hand side of the Navier-Stokes equation, dP by dx is positive, this quantity on the left hand side starts to go on decreasing, and therefore, you would reach a stage where the flow is no longer able to sustain itself, and therefore, you would see separation of flow occurring. So, this is a very, very important case, and this happens to be the limiting case. So, limiting case of wedge flow solution beta is equal to minus 0.2. Any beta less than minus 0.2, flow separation occurs. Once flow has separated, boundary layer equations not valid anymore. Therefore, beta greater than minus 0.2, beta equal to 0, beta equal to 1, beta greater than 0. These would be cases that are important, and at an undergraduate level, this is flat plate. And when I do this flat plate business, if I go on to write the solution, f triple prime plus 1 half f double prime equal to 0, subjected to the boundary conditions that I just mentioned to you. I would get, this is given in most undergraduate textbook, this is called as a Blasius solution, and the Blasius solution would be such that you would have a table of eta, f prime of eta, f double prime of eta, and f of eta. So, you go from eta equal to 0, 0.1, 0.2, all this way 5, all this way up to whatever number, 10 or 20, whatever you want. What is this infinity? Remember, one of the boundary conditions is this. Let us look at this a little carefully. Y equal to infinity, eta equal to infinity. I don't know what is this infinity. I know y equal to, this is a parabolic equation. So, I march from y equal to 0 or eta equal to 0, and then I progressively increase my eta. My boundary condition, that value of eta, I take steps in eta. Okay, eta equal to 0, next would be eta equal to 0 plus delta eta. So, I get a new eta or a new eta, I substitute and solve the equation, I get f f prime, f double prime at the new eta. That value of eta, I continue to march in eta. I continue to march in eta such that at one value of eta, which I do not know, it will so happen that f prime of eta would be equal to 1. This boundary condition would be satisfied at one particular value of eta, and beyond that, any value beyond that also f prime of eta would be equal to 1. What does that mean? It simply means that u has become equal to u infinity and I continue to remain at u infinity even after that, right. This is delta. So, beyond the boundary layer, y times u infinity by nu x eta, right. So, beyond eta equal to that value, u is equal to u infinity, that means f at this value and beyond is 1. So, that value where u infinity is reached for the first time is chosen as that so called infinity. I hope this is clear. Infinity is not some number which is very huge in this case. All it means is you are trying to march along the eta direction. March along the eta direction means you move from y equal to 0 or eta equal to 0, go to next progressively march above the solid surface. That value of eta, that value of y, where u becomes equal to u infinity corresponds to the location of so called infinity, where the boundary layer edge is there. And therefore, if you generate a table like this of eta, f prime, etc. for this ordinary differential equation, this can be solved by Runge-Kutta method or any such ODE solver. If you solve this, you will generate a table of results. So, you get for eta equal to 0, f prime is 0, f is also 0, f double prime is 0.33205. Next number is 0.33205, f prime is going to be 0.3321, f is going to be 0.00166, and you generate this table. At eta equal to 5, you get f prime, this f prime is 0.99154. This is f double prime is 0.01591, f of eta is 3.28327. What is important is this quantity, f prime. What was f prime of eta is u over u infinity. When eta equal to 5, u by u infinity is this number 0.99154. So, this number eta is 5 can be is equivalent to infinity for us. Is equivalent, it is not infinity, it is equivalent, it plays the same role as infinity. That means, if I go beyond 5, 5.1, I might get 0.9935 whatever, 5.2 I might get 0.9942 something. What I am trying to say is, going higher and higher in eta beyond 5 does not help us much, and therefore, you can stop at eta equal to 5, which corresponds to f prime of eta, and this is a very important result. What we say, u by u infinity is equal to 1, approximately 1 for eta is equal to 5. Boundary layer thickness is what this is, right? Boundary layer thickness is defined as location where u is approximately equal to u infinity. So, therefore, eta equal to 5 means our definition of eta, y u infinity by nu x is equal to 5. What does that mean? This y now is your delta. correct. This is my delta. Boundary layer thickness delta is defined as the location where u is u by u infinity equal to phi. Therefore, delta, let me just divide by x, is equal to 5 divided by u infinity by nu x. I have divided by x here, so I divide this also by x. Therefore, delta over x is equal to 5 divided by u infinity x by nu under root. This is 5 divided by r e to the power half. Therefore, delta by x is equal to 5 divided by square root of Reynolds number. So simple and elegant. When we use scaling analysis, we said delta is of the order of re to the power minus half. Today, with this manipulation, we got delta by x is equal to 5 times re to the power minus half. That coefficient order was replaced by an equality, and that coefficient came by this analysis. Next, when we do integral method, I am just going to write that here in the next set of lectures. When we do integral method, we would get delta by x is equal to some c times re to the power minus half, where c1 depends on complexity of the profile. So, it could be 4.64, 4.72, 4.9, whatever. All I am trying to say is the functional relationship of delta is still maintained. And who gave us that for the first time? Scaling analysis gave. So, this was great. This is betterment to get you numbers. This is also another method to get you numbers. So, the point to note is scaling analysis was a tool for me. And if I didn't know this functional form, I would be groping in the dark and I would not know how delta is going to vary. Now, even before I go and solve a differential equation or assume a profile, I know that delta has to vary this way. I know the nature of the solution. That is the beauty of scaling analysis. Now, let us write CFF of x. As engineers, we need to know coefficient of friction. So, that is tau wall x divided by half rho u infinity squared, which is nothing but mu du by dy at y equal to 0 divided by half rho u infinity squared. I substitute for du by dy, that is going to be mu into du by dy is du by d eta times d eta by dx at y equal to 0 divided by half rho u infinity squared. This is du by d eta is mu u infinity f double prime of eta. D eta by dx is going to be u infinity raised to half divided by nu x divided by half rho u infinity squared. This on simplification gives me 2 nu over u infinity nu x f double prime of 0. You can just simplify. This is all at eta equal to 0. So, this is 2 nu by u infinity nu x, and if I just simplify this one more step, CFX is equal to 2 f double prime of 0 divided by u infinity x by nu under root, which is nothing but 2 f double prime of 0 divided by re x to the power half. Coefficient of friction is this expression. Delta by x was 5 over re, this one, Reynolds number to the power half. And what is the additional thing? This one. So, if I go back to my table which was generated, this table would give me, this table is going to give me f double prime of 0 f double prime of 0 was this 0.33205. So, if I substitute for that, I would get f double prime of 0 is 0.33205. This implies coefficient of friction, local coefficient of friction comes out to be 2 times 0.33205 divided by R e to the power x, implies Cf of x is 0.664 divided by Reynolds number to the power 1/2. Coefficient of friction is known, therefore shear stress and hence the drag force can be obtained. Shear stress or the drag force can be obtained as follows. So, tau wall of x is nothing but this one, tau wall of x is nothing but mu du by dy at y equal to 0. This would come out to be, you substitute exactly like before, you substitute for that here, du by d eta by dx, you end up getting tau wall of x is 0.332, this is mu u infinity raised to 3 by 2, this is just maths, and using du by d eta times d eta by dy, d eta by dy, sorry, d eta by dy. So, d eta by dy. So, this is going to be 0.332 u infinity raised to 3 by 2 rho to the power half mu to the power half divided by x to the power half. This is all manipulation. This one was from table which we had generated 0.33205. So, therefore, given fluid and given free stream velocity, given fluid and u infinity and x location, tau wall can be calculated, or tau wall is proportional to 1 by root x, x to the power minus half, and we told this before. Laminar flow, wall shear stress local, and this is how your boundary layer was growing, correct. So, wall shear stress is this blue curve. Wall shear stress varies as x to the minus half, and now you can use this same expression to calculate drag force. Fd is equal to, you will get integral 0 to x tau wall x times b dx, which is your area, that would happen. Therefore, you would get drag force is nothing but 0.664 b u infinity raised to 3 by 2 mu to the power half rho to the power half x to the power half because of the integration. So, drag force is proportional to root x. This is if you take only one surface. So, you have drag if this is solid and you have only flow this way, boundary layer developing this way. If you had a plate and the flow was happening such that you got boundary layers on both sides, u infinity was this way, such that you had boundary layers on both the surfaces, multiply by factor 2 for 2 surfaces. Lastly, drag coefficient is nothing but CD is drag at x equal to L divided by half rho u infinity L into BL. This is the definition of drag force. So, this if you substitute drag, local drag expression, this is this Cfx. So, you substitute for this, this will get x is equal to L. I will get CD equal to 0.664 b u to the power 3 by 2 mu to the power half rho to the power half L to the power half divided by half BL rho u infinity squared. This is nothing but 1.328 mu rho u infinity L, which is nothing but 1.328 by REL, or nothing but 2 into 0.664 by under root REL. What is this? This quantity is nothing but coefficient of friction at L. So, drag coefficient is nothing but 2 times local skin friction coefficient. CD is 2 times local, that means at that location. This is drag over, two different things. When I have subscript L it or subscript X, it represents local, Reynolds number local. When I want to calculate the average over that length, so this is local, this is local. When I do 0 to X, that means it is average. This is at X, it is called local. Integrated would have bar, over bar on it. So, CF bar, CD bar, this is average value. So, average value of coefficient of drag CD is 2 times CF at local value. This is something which is also seen in fluid mechanics. Exactly the same analogy will be used for heat transfer. In the subsequent modules, we will do the similarity solution for the energy equation and look for its interpretations. Thank you.